Good evening, everyone. So today we will be discussing fluidized bed and packed bed conditions. So before starting today's class, I can wait few more minutes for people to join for the class today. Then we will start. Okay, so we can now start for today's presentation. So welcome to today's class. I'm Smita Mondal. I'm PhD PMRF scholar in Department of Chemical Engineering, IT Madras. So today we'll be discussing one important mechanical unit operation, that is flow through packed and fluidized bed conditions. Starting with basic introduction about today's class. So we will be discussing on particulate solids. So when particulate solids, they are packed within a container, they form an arrangement allowing for the void space between the particles to be filled by any gas or any other fluid. Such arrangement generally has referred to be as bed condition, and the interactions between those solid particulate matters and the void filled with air are related by an important property which is known as porosity. So what is there if you have the bed and there are so many of particles, they are making a bed in a reactor. So you can see these are some irregular shaped or some specific shaped particles. They are inside the reactor. So when when any liquid or gas is flowing, so it will pass through the void space and it will go up. So this space is known as bed porosity. So this porosity we are talking about, this is nothing but the bed porosity, because the solid particle, if it is porous even, they are not that much efficient to pass through the liquids. So we are talking about external porosity, which is bed porosity. Now uh, any particular fluid that we are considering here, if they are at very low velocity through the porous bed of solid material, suppose a packed tower that I have just drawn here, uh, doesn't cause the particle to move if the velocity is very less. The fluid will pass through the small and tortuous channels. At that point, there will be some reduction in the pressure energy. Thus, when the fluid is flowing through the stationary granular particles, they cause the pressure drop in the bed, and it is important to predict that pressure drop across the bed due to the resistance which will caused by the presence of particles. If we are considering if the fluid flow rate in the bed if the fluid flow rate is Q, that is volumetric flow rate meter cube per second, and the bed cross-sectional area is capital A, which is meter square, then superficial velocity, or which is also known as empty bed velocity, U naught, is defined as U naught equals to Q by A, which is meter per second. Now, examples of such fixed bed operation include catalytic reactor, adsorption columns, ion exchange columns, any kind of sand filter, or any kind of this kind of particulate filters are also uh, we are discussing. So when we are discussing these concepts, try to um, try to understand these kind of concepts are very required when you are dealing with this kind of catalytic reactions in a huge reactor, also adsorptions performance we are doing. So this kind of um porosity, porous space material, how we are going to calculate the fluidization velocity, this kind of thing will appear. And it is important to know what is the velocity required for particulate zone. So if the fluid velocity through the bed of particulate solids is steadily increasing, a point will arrive when the particles no longer remain stationary, but they are fluidized under the influence of that fluid at that particular velocity. So that point, it is known as the fluidization point. During the past 5 decades, fluidization technology has been extensively applied to various chemical processes. It provides better and uniform heat and mass transfer between the fluid and the solid compared to the conventional packed bed or moving bed unit operations. So, in today's class, we will be discussing the packed bed conditions at initial, and then we will be gradually moving towards the fluidized bed concept. So, there are some common industrial processes. They use the fluidization technology like drying, catalytic cracking, chemical synthesis, adsorption desorption process in presence of the packed bed, gasification, pyrolysis, granulation, calcination, combustion, coating, bioreaction, polymerization, beneficiation of coal or coking. There are many kind of examples that we are dealing with: packed bed, fluidized bed, bubbling fluidized bed, this kind of reactors. So now we are going to discuss about Darcy's law, which is very important when you are dealing with porous bed. So you have to know the basic rule of Darcy's law. So Darcy's law is a principle formulated by Henry Darcy, which explains the movement of the fluid through the porous material. So here in this picture you can see that you can see that there are porous material that is packed in a bed and the fluid is going from top to bottom direction. So the height difference here we are considering h1 minus h2 as h1 and the length of the porous bed is del L. So Darcy's law is applied for movement of the fluids through the porous material that we are dealing here. The pressure drop del P per unit length of the bed, that is L, is proportional to the superficial velocity u0. Now you have to remember that superficial fluid velocity is the empty bed fluid velocity. That is nothing but the velocity inside the reactor when there is no bed material. Now this is proportional, that del P by L, which is proportional to superficial fluid velocity. Now here the constant that we are when you equate these two, there will be one constant K into u0. Here K is the permeability coefficient. So this permeability coefficient is a function of particle size as well as what kind of packing material you are using. That is also important for considering the permeability coefficient. Now there is linear relation between the flow rate and the pressure difference leads to the assumption that the flow is laminar and expected that the Reynolds number for the flow through the pore spaces in a granular medium is low, since both the velocity of the fluid and the width of the channel is usually very small. So with this assumption, there is Darcy's law equation is evolved, and also they have considered the effect of viscosity of the fluid. So the final Darcy's equation is known as Q equals to K by mu del P by L, where Q is the flux and K is the permeability coefficient, mu is the viscosity, and del P by L is the pressure drop per unit length of the bed material. So we are moving forward with the idea to discuss about the channels through packed bed of solid particles. So you can see in this picture that these uh, yellow grains symbolize the solid particles, and we are flowing the blue color fluid. It might be maybe you can consider liquid. So you can see that they pass through the bed of these solid particles where it finds the space. Now this kind of pore space that we are talking about, this is uh, external void or external porosity. That is also only known as bed porosity. Now, there are certain cases occurs that there are some spaces where completely empty pore space is present, and sometimes when the fluid is passing through the pore spaces, then it is tortuous fluid flow path they make. So in a porous medium, we have distinct entities, basically two. One is the solid grain, another one is the pore space. Unlike any flow through pipe. So here we want to discuss about equivalent channel diameter, because when the fluid flows through the porous material, they form certain channels. Now we are considering these channels to be, assuming these channels to be a um bundle of tubes. So this With this assumption, we will develop the equation for equivalent channel diameter. So it is calculating based upon the assumption that the bed has a set of uniform circular channels, and the total surface area and the void fractions of those channels are also included in those equation. So obviously when there is bed, so total surface area of that bed will be number of particles uh, into surface area per particle. So for irregular shaped particle, we already discussed in the very first class that the property of the particle, where uh, we have calculated the surface to volume ratio for sphere, or we have also learned about sphericity concept for irregular shaped particle. So we will apply those concepts here in the equation development. So the actual particle packed bed is approximated as a bunch of n number of capillary tubes which are packed together, and fluid is flowing through the capillaries. Now the surface area of n number of such parallel channels of each of length L will be surface to volume ratio into volume of each particle. So we have to uh, we have to understand that how we are going to calculate the surface to volume ratio for regular shaped spherical particle. That is surface area of the sphere by volume of the sphere, which comes to be 6 by dp. But when we are dealing with irregular shaped particle, then the sphericity phi s will appear. And for your information, we have already discussed sphericity equals to 1 for a spherical particle. So here it comes the porosity, which is denoted at this symbol. This porosity or pore space, it is of the bed, so the particle volume will be 1 minus of this porosity. So thus the void volume in the packed bed is equivalent to the total volume of n number of channels in the bed. Now we are going to derive the equation for equivalent channel diameter. So here we already have the equations that we have developed, that surface area of n number of channels, that is n into surface area of those channels, which will be equal to surface to volume ratio for any irregular shaped particle, which is termed as this, into volume of the particle. Now the volume of the particle is total cross-sectional area of the bed into length, that is meter cube, into, it denotes the particle volume. Particle volume. So this equation, where S is the cross-sectional area of the bed. So by solving this equation, this is equation number 1, and also we have just defined that void volume in the bed is same as total volume of n number of channels through which the fluid is passing. So this one is equation 2. Now this by solving these two equations, we will get an ultimate equation like this is the uh, simplified form we are getting from these two equations. So this is how we derive the equivalent channel diameter in the packed bed condition, where it related to the bed porosity, sphericity of the irregular shaped particle, and the diameter of the particle. Now, if you have, suppose for a spherical, for any spherical particle, this phi s will be 1, and through the literature, the porosity is around, suppose, 0.43, then the equivalent will be 2 by 3 into 0.43 by 1 minus of 0.43 into dp, which is nothing but 0.503 dp. If the spherical particle it is not, it is irregular shaped particle, then it will be another term will present. I hope this is clear to you. Next, we are going to discuss about pressure drop in a packed bed situation. So there are a few equations that we are going to focus today, which are very important for calculating pressure drop. The first one is the laminar flow condition in the packed bed, that is related to the Kozeny-Kármán equation. This equation is valid when the particle Reynolds number is less than 1. What it does, It shows that volumetric average velocity of the fluid through the channel within the bed is u, and the velocity of the fluid stream just before entering to the first layer of the solid is u0, which are related by the porosity. So it denotes that volumetric average velocity is equals to superficial velocity by porosity. Now we are going to focus on Hagen-Poiseuille equation. Now this equation we are using because we are considering that a straight line or straight tubes as a packed bed. So when there is laminar flow in a straight tube, we generally represent the pressure drop in the straight tube by this equation of del P is equals to 32L U by mu by d square. Now for this case, if you just rearrange this equation, you will get del P by L equals to 32U mu by d equivalent, that square. Now you already have the you have derived what is the expression for equivalent. Now this u0 equals to u0 by mu, so it will be superficial velocity by porosity and this. And in this equation there will be one extra term which is this one. It denotes that it is a tortuosity factor, and there is correlation which denotes that the constant 150 will be incorporated from that equation. It is the correction factor for tortuous path and non-straight and parallel channels. So from there are several experimental studies. From there we have so you can see, like, after simplified this form you will get del P by L equals to 72. So in this equation from the and this one is correction factor. This one is correction factor for tortuous path, and non-straight and parallel channels. So from the several experimental conditions, empirical constant 150 is for 72 lambda 1. So from there we will get the ultimate equation, that is del P by L equals to 150 U by pi s dp square 1 minus this by this. So this one is very important to understand, that this equation that we are talking about, this equation is known as Cogeny Karman equation. And most importantly, it is only applicable for low Reynolds number. So this part, this equation is only focused on viscous loss, related to the viscous loss. And then when we jump to the next part, which is like turbulent flow packed bed, for that case there will be Barker-Lambert equation, which is turbulent flow. Reynolds number is greater than 1000. For that case, the pressure drop equation will be del P by L equals to 2 friction factor rho into average velocity by D equivalent correction factor. Also, you replace D equivalent in this equation. So ultimately you will get because U equals to U naught by this, that we already know. I am not doing substitution here. So in this equation also this lambda 2 is the correction factor. So following an empirical equation for pressure drop in the packed bed condition for turbulent flow, empirical equation, they give the relation between these two, and it produces the Barker-Lambert equation. The next part is comes that pressure drop in a packed bed situation when we are considering the pressure drop in a entire range of flow rates, assuming all the viscous laws and kinetic laws are additives. So till now, this Argand equation can be just be summation of these two that we have just derived, that del P by L equals to 150 mu u phi s dp square 1 minus plus 1.75 u naught square by phi is dp 1 minus this by this cube. So this whole equation is Argand equation. It is known as Argand equation. So here this part is Cogini-Kármán equation and this part is Barke-Plummer equation. So this part is referred to the is related to viscous laws and also it follows the Stokes law regime, whereas this part is related to kinetic laws and it is related to Newton's law regime. So this Argand equation can also be represented in the form of dimensional non-dimensional form. We can also represent it. So now we will focus on how the Reynolds number and friction factor are related in the packed bed condition. In this Argand equation, we can simplify it taking common from this equation. This is known as particles Reynolds number. And now it is friction factor if is denoted as del P by L into d rho dP So ultimately our equations become so the non-dimensional equation of the argon equation is denoted as this. Friction factor Now, in today's class, um, we will be solving our first numerical. The first numerical shows that air having density 1 kg per meter cube, viscosity is 1.35 10 to the power minus 5 kg per meter cube, is flowing with a velocity. So the air is flowing with a velocity of 2.5 centimeter per second through a packed bed of powdered material. Pressure drop across the bed is given. This 104.6 Pascal and the bed porosity is 0.43. You have to find out the particle size or diameter of the powdered material. Consider it to be spherical and assume the Kozeny-Kármán equation is valid for this fluidism. Also consider the packed bed height is 1 meter. So to solve this equation, as the given data here, density of the fluid is 1 kg per meter cube, viscosity of the fluid is 1.35, making it in SI unit, it will be also del P is Pascal, L equals to 1 meter, bed porosity is 0.43. And you have considered spherical particle, the sphericity is 1. It is already noted that you have to use Kozeny-Kármán equation So that equation tell you del P by del L, only the first part. You just put all the values and you get the value of dP. You have to report the value of dP in millimeter. So it is very simple. You will put the values. So this is the answer. Hopefully you will get this answer similar to my solution. So we will now solve the next question for today's session. Let's see what is the question. This consider a bed packed with a sphere of diameter 1.1 millimeter whose void uh, fraction is 0.43. What is the average velocity of the fluid flowing through this bed if the empty tower velocity is 1 meter per second? It is very simple and a small problem. Here the given data are empty tower velocity, that means superficial velocity, void is 0.43. Now you have to calculate the average velocity. U equals to so this one is the answer. Hopefully you got the same answer. We will move to the next question. Consider a column of diameter 0.61 meter and height 2.44. Spheres are having diameter 12.7 have been used to fill the column in order to make a backbed. A fluid of density and viscosity are mentioned flowing through the packed bed at a mass flow rate. Then what will be the Reynolds number? So let's solve this question. Diameter of the uh, so here the given data, diameter of the column is this. Particle diameter fluid density fluid viscosity mass flow rate of the fluid. You have to find out the Reynolds number. At first we will calculate that what is the what is the cross sectional area of that column. Pi by 4 dc square. Then you should calculate the value of volumetric flow rate, that is mass flow rate divided by density. From that you can calculate the velocity. If you know the velocity, then you can easily calculate the Reynolds number. So this is the Reynolds number is calculated. Now let me know by this Reynolds number, what do you think that it will be in the laminar, turbulent or transitional zone? Obviously, by this value, we can see that this is the transitional flow regime. Then we will solve our next question, which is very easy. Just you have to put the values in the equation and you will get it. So the question, it says that a liquid of density 750 and viscosity is given. It is flowing with superficial velocity through packed bed. Density of the particulate solid and diameter is given. Porosity is also given. You have to find out the Kozeny-Kármán equation and the Barke-Plummer equations, the ratio. So I hope you have the equations, Kozeny-Kármán equation and Barke-Plummer equation. You have to just write down the equation and simplify it in the form of the ratio. Now you solve this equation and you will get the simplified form. Now you have all the values. Here the given data So you have to just put this equation, these values in this equation, and you will get the ratio. Let me know what you are getting the ratio value. So you will, after putting all this value, you will get 16.57 as answer. Next part we are going to learn about fluidization. So when a fluid at low velocity is introduced into the bed of solid particles, fluids hardly percolates in between the space present between the solid particles. When with an increase in the fluid velocity, a point achieved where all the solid particles are suspended by upward flowing fluid, the bed at that stage is called minimum fluidization. The velocity with which the bed fluidizes is known as minimum fluidization velocity. Any other velocity with which the bed fluidizes is known as fluidization velocity. So what is the difference between minimum fluidization velocity and fluidization velocity? When you add excess velocity with minimum fluidization velocity, you will get complete fluidization velocity. So it is obviously a very uh, it is a case of fluid solid flow, and where the fluid through the fluid flow, it the bed of the solid particles, they provide the resistance, and there is, as a result, there will be total drag due to the particles present in the bed. So when we talk about fluidization, at the point of fluidization, the fluid-like properties we can observe for the bed particles. You can see in the video here, when the fluid is introduced, the settled bed is completely fluidized after a point. This point, it fluidizes. So this velocity, with increase in velocity at a point, reaches when the velocity is sufficient enough to fluidize all the bed materials. At that point, the properties of that bed will be similar to the fluid property. The surface of the bed becomes horizontal, and if it is disturbed, it can return quickly to the horizontal, like a liquid, like a fluid. Like in a liquid, the pressure increases with depth. In fluidization bed also, it is the same condition. Objects of lower density will float on the surface of the fluidized bed, whereas objects with higher density will sink to the bottom of the fluidized bed. So if a hole is open on the wall of the container vessel of the fluidized bed, if hole is open, then the particles will pour out a jet similar to the water. So it behaves like a fluid. And the bubbles arises through the fluidized bed. They will also burst on the surface as a liquid, and moreover the bubbles shape and rising velocities are similar to those of the bubbles in liquid. So by this we got to know that fluidized bed also behaves like a fluid. That's why it is named as fluidized bed. So we are now going to discuss about the fluidized different regimes. So if the flow is a streamline, a straight line of slope unity is obtained at a very low velocity. So this it is a straight line with uh, at a low velocity part. So this one is fixed weight. At fluidizing point, the pressure gradient begins to fall because the porosity of the bed will increase, and the fall continues until the velocity is sufficient enough to transport the solid out of the bed, that is illustrated. The pressure gradient then starts to increase again because the frictional drag will present that will frictional drag of the fluid at walls of the tube starts to become very significant. A minimum fluidization velocity will mark a transition from fixed bed to fluidized bed condition. At the minimum fluidizing velocity, it may be expected that the flow relations for the fixed bed would be applicable to the fluidized bed also. At the opposite limit, when the bed is fully expanded so that its voids approaches to unity, it consists effectively of solid single particles suspended in the fluid, and thus any relationship describing a fluidized bed should extrapolate at unit voidage to one application to individual particle. So there is an at intermediate condition where the particulate fluidized bed is hydrodynamically similar to the sedimenting suspension. So here more accurately you can see in this picture that packed bed becomes bubbling regime, and then it goes to slugging regime, and then turbulent and fast fluidization regime, and then pneumatic transport. This is the aggregative fluidization is happening this four regime, that is non-homogeneous, and it is happening with increase in the gas velocity. So we can discuss that what is happening in the picture, that the behavior of the bed after minimum fluidization depends on whether the fluid is liquid or gas. Suppose you are passing through liquid, so as the upward flow of the liquid increases, the packed bed continues to expand uniformly and homogeneously with increasing the interstitial void space until the particles are eventually carried away or illiterated. This kind of fluidization is known as homogeneous or particulate fluidization. We will discuss it later also. So when the fluid is gas, The excess gas may manifest itself as bubbles. The bubbles will result into two distinct phases within the bed and give an appearance of non-homogeneity into the system. Such a behavior is known as aggregative or non-homogeneous fluidization, also known as bubbling fluidization. So this transition from the packed bed condition to either particulate or aggregative fluidization of gas-solid system depends on the particle, also the gas property. To develop the fluidized bed process for gas-solid system, the ability to predict the flow behavior and the calculate essential operating parameters like fluidization velocity, minimum condition, flow regimes, bubble characters, etc. are more critical. As the gas flow rate further increased in the bubbling gas-solid fluidized bed, the bubbles collides and may grow larger as they migrate to the bed surface, and with coarser and granular solids, or they achieve a stable size with fine powder. The passage of the bubbles through the bed will result in mixing and churning of the bed material, which creates uniform conditions within the bed. But if the bubbles get larger than two-thirds of the bed diameter, then the slugging condition may appear. Slugging conditions can cause severe pressure fluctuations and bed vibration as well, along with significant reduction in the heat and mass transfer efficiency. Further increase in the gas flow rate and onset of turbulent regime will appear, where disappearance of the distinct mud bed surface will be observed. At this point, the void spaces and the particles form co-continuous phase. At higher velocities, the contents of the bed are elucidated, thereby resulting in partial depletion of the bed material. So, in details, we are going to discuss that how the behavior of the bed particles is happening in a fluidized bed. So at first, when there is no flow, the pressure drop is zero, and the bed had certain height. As we proceed along the right arrow in the direction of the increasing superficial velocity, the tracing path ABCD, the pressure gradually increases and then becomes constant, while the bed height is almost fixed at that up to that point. This is the reason where Argon equation for packed bed can be used to relate the pressure drop to the velocity. So uh, when this B point is arrived, the bed starts expanding in height while the pressure drop levels off and no longer increases with the increase in superficial velocity. So at that point, when the upward force exerted by the fluid on the particle is sufficient to balance the net weight of the bed, and the particles begin to separate from each other and they float in the fluid. As the velocity is increased further, the bed continues to stand to height, but pressure drop stays constant. But after that point, the bed height expands. It is possible to reach large superficial velocities even without having particles carried out with the fluid at the exit. This is because at that point the settling velocity of those particles are typically much larger than the largest superficial velocities used. So now gradually decreasing the superficial velocity in the direction of the reverse arrow in the figure, we can see it follows the curve DCE. At first the pressure drops stays fixed up to a point in between B and C, and the bed height no longer decreases while the pressure drop follows the curve CEO. So a bed of particles left alone for a sufficient length of time becomes consolidated, but it is loosened enough when it is fluidized. So after fluidized, it settles back to more loosely packed state. This is why the constant bed height of the return loop is not possible over the period, and it is always larger than the bed height at the initial. So thus we came to point that there is one certain velocity in the superficial velocity where the uh, pressure drops becomes constant, and from where the uh, bed rises enough. This is the point C is the point where the minimum fluidization velocity is occurring. So how mathematically you are going to express that one? That when the minimum fluidization condition occurs, it will balance the net weight of the bed against the upward force exerted on the bed. So at minimum fluidization condition, the upward force on the bed is del P into A. If the height of the bed at this point is L, and void fraction is this, then what will be the volume of particles? That is 1 minus of this into A into L. Now there is a net gravitational force acting on the particle also. So now we will talk about the inception fluidization, that is the homogeneous one. No, inception fluidization is onset of fluidization. So typically for a bed of smaller particles of size less than 0.1 millimeter, the flow conditions at this stage such that the Reynolds number is relatively very small, less than 10. So there the Cogini-Karman equation will be applicable, as that will be the viscous flow regime. So on the point of onset of fluidization, according to the um, um, Cogini-Karman equation, uh, we can write the fluidization velocity is in this term, When the superficial velocity becomes equal to fluidization velocity, that state of bed is referred as inception fluidization. Now for any void fraction in that stage depend upon material, shape and size of the particle. For nearly all the spherical particles, the void fraction lies between zero point 0.4 to 0.45. A larger particle greater than 1 millimeter, the inertial effects are very important. That is, so that time full Argon equation, including the Barke-Plumber equation, should be used to calculate the fluidization velocity. Now, considering the condition, we must impose the superficial velocity so that the particles are not carried out at the fluid exit. This would occur if the superficial velocity is equal to the settling velocity of the particles. Now we are considering the smaller particles in the regime of Stokes law. So from there we can calculate the settling velocity as from this equation we can calculate this. So what will be the uh, ratio of this? It is 25 by 3, 1 minus of porosity by porosity Q. So when for the spherical particle the porosity lies between 0.4 to 0.45, this ratio will yield from 78 to 50. And according to McCabe and others who did the experiment, and they suggested to common practice to operate the fluidized bed at a velocity as high as 30 times higher than the inception fluidization velocity. Now we are going to solve the last numerical, not last. Okay, let's solve this numerical which is related to fluidization velocity. The column diameter, and it is dealing with packed with glass spheres. So you have to calculate the pressure drop at a minimum fluidization condition. So at a minimum fluidization condition, um, we follow this equation. So here we have to calculate the pressure drop. So this is the equation that this is the pressure drop for at a condition of minimum fluidization velocity. So now we are going to discuss about particulate fluidized velocity. This is the conditions of the homogeneous fluidization. You can see low velocity, it is fixed rate. Slightly higher velocity, it is reaching to the minimum fluidization. Liquid velocity more at a more higher speed, it is reaches to the homogeneous fluidization, so it is particulate fluidization. But when you are dealing with gas, then it may forms the bubbles, so it will give you the aggregated or non-homogeneous fluidization. So at this point we are discussing this part, particulate fluidization. So fluidization can be broadly categorized into two parts. One is particulate, another one is bubbling. Particulate fluidization occurs when you are dealing with liquids. As the velocity of the liquid is increased past the minimum fluidization velocity, the bed expands uniformly and uniform conditions prevail in the liquid-solid mixture only. So, in that position, you can see that so if the height expanded is L, so we can write two equations here at a condition expanded condition and another condition is minimum fluidized bed condition. So when these two can be equated, from there we can have LE equals to LM 1 minus. So this in this equation, to calculate the expanded height of expanded bed, at particulate fluidized bed condition, you want to get the you have to get the value of porosity under the expanded condition. And uh, to calculate this porosity, we are having this equation. This empirical uh, equation is this, where this m value we can get from the graph of m versus Reynolds number. So this one is the graph for m versus Reynolds number. So for a you can calculate the Reynolds number. Suppose it is following this region. So from that you can have your m value, and if you get the m value, you can get, and you also know the superficial velocity, you can get the value of the void at the expanded condition, and you can use the last equation to calculate the height of your fluidized bed. Let's solve one question, and it will be more clear to you. The bed is made by filling a column of spherical particles, the bed is fluidized with the solution of viscosity and density mentioned. What is the voidage at 25% expanded bed conditions? If the void at the fluidized bed condition is okay, so we can have this equation. So it is 25% expanded, which means this ratio is 25% more. So from there, the porosity becomes 5:2. Very easy. At the last concept, we are going to discuss about the bubbling fluidized bed. So you can see that rising bubbles when you are introducing gas to the system. In the solid particles, gas bubbles will sometimes they follow and collides, and at the surface of the bed they are even rupture, so they can burst. You can see they can burst and onto the surface of the bed. So in contrast to the particulate fluidization condition, bubbling fluidization occurs when it is gas fluidized bed and the bed is fluidized and large pockets of gas-free particles are seen to rise through the bed. Where there are particles, the bed void fraction is approximately the value that prevails at the point of the inception fluidization. The bubbles will grow until they fill all the cross section, and then successive bubbles move up of the column and conditions. This is known as slugging. Sometimes very dense particles in the liquid can show bubbling, and the gases at high pressure when flow through the beds of fine particles can also give rise to the particulate fluidization sometimes. Usually this occurs when it is at a very lower velocity and very high velocity, then the bed shows bubbling. This aggregative fluidization occurs with all the solid gas system, sometimes with solid liquid system, but for the very high density solid. The growth rate of the smaller bubbles will generally be greater in the gas solid system than that of the solid liquid system. So here we can see that the gas flow through the dense phase will be assumed as uh, so here for bubbling fluidized bed condition, we can have the gas flow where Fp is the fraction of bed occupied by the by bubbles, and this one is the bubble velocity. Thus, we can also have the similar correlation and from there we can have. So this is what for today's class. We have discussed about bubbling fluidization conditions as well as particulate fluidization condition. So we have also solved few numericals. So hopefully it will help you to solve and for your assignments for this week. And in the next class we will discuss about the filtration part. That is one important mechanical unit operation for filtration, that is solid liquid separation. There will be so many of equipment involving for that case, and most importantly that anything that you, if you have any question or doubt, you should join your these live sessions from whenever you want to fill. And I have tried to cover some numericals which is directly from the assignments, and mm, some extra numericals that I have solved in today's session. So if there is any doubt regarding my lecture, then you can raise question in the question answer platform there. So that's it today. I will like to end this session here. We will meet next week. Thank you.